This is Unit 2, Lesson 3, Part 2. Topic 2.3, Estimating derivatives of a function at a point. So we're going to start with an example. We're going to consider the radical function y equals the square root of x. So what we want to do is we're going to go through the steps to find an equation of the tangent line, which would be a linear approximation of the curve at x equals 9. And then from there, we're going to see, what if we're a little off 9, like 9.1? It's hard to take the square root of 9.1, but it would be easier to find the value from a linear equation than it would be from a square root. So that's what we're going to do. So we're going to use the difference quotient to find the slope of the curve at x equals 9. So that means we are going to take the limit as h approaches 0 of f of 9 plus h minus f of 9 all over h. So substituting into our square root function, we get the square root of 9 plus h minus 3, because we substitute 9 in, we get 3 over h. And now I'm going to use the conjugate to get rid of the h out of the radical so I can eliminate the h in the denominator. So I'm going to multiply top and bottom by 9 plus h plus 3 over the square root of 9 plus h plus 3. Okay, so that's going to give me the limit as h approaches 0 of 9 plus h minus 9 over h times my conjugate. So 9 plus h and then plus 3. Okay, so simplifying the numerator, which is exactly what I wanted. So we take the limit as h goes to 0. We just have an h, which we will cancel with that h in the denominator, and we'll be left with the conjugate here, which is great. So those will cancel. So we get the limit as h approaches 0 of 1 over the square root of 9 plus h, and then plus 3. And now we can do a direct substitution. So we get 1 over the square root of 9, because h is 0, plus 3. So this gives us 1/6, because we'll have 3 plus 3. So there's the slope of our curve at x equals 9. So now we're going to write the linear approximation of f near x equals 9. So we have y equals the slope of our tangent line times x minus the value of the function right at 9. So instead of trying to substitute 9.1 here and try to take the square root of 9.1, I can substitute it here in my linear approximation, because that's what we're calling it. It's approximation of the curve near 9. So we're going to use that equation without a calculator to see how we get that. All right, so here's what's going on. We're going to have y equals 1/6 times 9.1 minus 9 and then plus 3. So this is going to be 1/6 times 0.1 plus 3. Now what I did is I have 1/6 times 1/10 plus 3. So I have, when I add this together, I get 3 and 1/60. So this is approximately equal to 1/60. So you can take 100, divide that by 60, and you're going to get 3.0166. So we're saying this is approximately equal to f of 9.1. Okay? So that's a lot easier than trying to find the square root of 9.1. So now let's graph the function in its tangent line and see what this looks like. And again, like in other videos, I'm going to try my best to get my tangent line to be exactly where I want it, but I can't really lay a a ruler down. So my square root function looks like this. It's 0. Whoops. At 0, I'm at 0. At 1, I'm at 1. At 4, I'm at 2. At 9, I'm at 3. And at 16, I am at 4. So I can draw a nice curve here. There's my square root. So this is y equals the square root of x. And then I'm going to draw a tangent line here at 9. Actually, that wasn't too bad. So here's my point 9, comma 3. And I can see that in that region that it is very, very close. They're really kind of touching each other right through there. That the linear approximation is very close to the curve. So that's not a bad approximation here. This is not a bad approximation of the value. Okay. So explain whether your answer to C is an overestimation or an underestimate for the actual value of the square root of 9.1. Justify your answer by reference to the behavior of the graph. Okay, so what we can say is that f of x is concave down, because it's like an inside bowl like this, so it's concave down. So that means the estimate has to be above it. Our tangent line is on the outside. So the estimate is an over approximation. Because the tangent line lies above the curve. Of the function. So knowing the concavity of a graph is very helpful to answer a lot of questions. Because remember, what we're really getting at with calculus is behavior. It is behavior. So then let's check and see how close we are. So I said you could use a calculator here. So the true value of the square root of 9.1 is to the same number of decimal points, exactly the same. So would your linear approximation formula be accurate to an accurate estimate tool of the square root of 5? Why or why not? Okay, so I'm going to just give you a second here to think about that. Now my answer would be no. And the reason for that is the square root of 25. So 25 itself is too far from where our linear approximation is located. Or as you could say, it's not in the local neighborhood. And yes, functions have neighborhoods. Okay? Because remember, it's only in that really small region that we can use a linear approximation. Okay, next example. We're going to use this graph, and it's a continuous function, and that is very important, of g of x to show shown to complete the table below. Okay, so here's some things we know. We know that the derivative of a function at a point represents the slope of the tangent line at the point, wherever we find the derivative. If we estimate the value of g prime for each x value in the table by drawing tangent lines through the given point of tangency, then estimate the slope of the derivative at the point. Then we're going to find the y-coordinate of the point of the tangent, and use the point slope form of the equation to write an equation. Okay, so that's a lot. So that's what we're going to do in the table. So we are going to use this approximation. So if you notice here, it's just rewriting our linear equation. This is like saying y equals y1 plus m times x minus x1, which was the original form that we gave for our point slope form. So it's the same idea. So this is the official way to write the tangent line approximation. Okay, so let's fill in the table. So we're going to have to slide up and down here somewhat. I apologize for that, or else I'd have to make it really small. All right, so the first x value is -3. So we want to estimate the derivative. So what we want to do is we want to, and it's right here in front of me, which is nice. I can see that one. So -1, 2, 3 is where point A is. So if I draw my tangent line through point A, it's going to be right, let me move that back up so I can see where I'm writing. Right along there, like that, okay? So this point is -3, -3, and if I count my slope, what I find is, let me draw this a little longer. So I can, because when I did it on paper, my line was really long, so I could see where my slope was. So that's not too bad. So when I found the slope, what I found is I go up 6, 1, 2, 3, 4, 5, 6, and over 1. So my slope is going to be, well, I'm actually going down. -6. My point of tangency is that point A, so it's -3, -3. Function behavior is decreasing because we're going down along A, so this is decreasing. And then the equation of tangent line is going to be y equals -6 times x plus 3 minus 3. Okay, I'm going to do one more, and then I'll let you guys do the rest, and I'll just show you the table. Okay, so the next one, it's at -2, which is point B. So for this one, I have a horizontal tangent line, and this point is -2, -6. So B is going to have an estimated derivative of 0, and my point of tangency is -2, -6, and it's constant at this point. So my y is just going to be a horizontal line, because I have a slope of 0. So the x term will just go to 0, because I'll have, in case you don't see that, I'll have y equals 0 times x plus 2, and then the -6, so all this goes. So I'll just be left with the -6. Okay. So you guys do the other 3 points, and then you can check your answer. So I'll pause the video. Okay, so here's the answers for the rest of the table. I also drew my tangent lines on my graph, and you'll notice we did not use points E and F. The last 3 sections of the table are C, D, and G. Okay, so now let's investigate slope graphs, or F-prime graphs. So let's do that next, which is the next page. Okay. So when you plot the motion of an object as velocity versus time, these are referred to as slope functions, or F-prime graphs. In the study of calculus and physics, you'll see a lot of what we're doing is highly interchangeable between the two topics. These graphs represent the rate of change of the original function. So by analyzing these graphs, you can find where the changes are occurring, whether they're happening slowly or quickly, by looking at how the slope changes of the tangent lines at specific moments in time. So for example 6, it says, consider the function shown below. Notice that the curve at the first point, x equals 1/2, the slope of the curve here appears to be about 1, and you can double check that by doing rise over run. Then at x equals 4, the slope has decreased to about 1/3. Can you analyze and sketch the slope of the graph on the grid? So, what would this slope curve look like so you can talk about what's happening with this function? And the answer to that would be, it looks like a decreasing exponential graph. So we have our slope here is 1 at 1, and then at 4, it was about 1/3. So this is what is happening. This is what the slope curve looks like. And if you notice, that's what is happening in our original curve. You have a very steep incline right at the beginning, which would be our very steep this way. But this steep incline gets less and less as we get to 1, just like this drops very quickly as we get to 1. And then the curve seems to flatten out quite a bit, which is happening here. And then as we go further, it's going to be even flatter. So that's why it matches an exponential decay. Okay? So let's compare these two graphs. So on the left, we have the graph of f of x, and on the right, we have the graph of f prime. Okay, so this graph is going to give us some insight, this f prime graph, to behavior of the original function. For example, at x equals 1, the slope on f of x appears to be almost -2. And then, if you look on the f prime graph at x equals 1, you can see that it is almost -2 right here. Right there. Okay, there's several relationships between the two graphs that are particularly important to note. Let's explore these features in depth. And it says, can you find those on your own? And I'm just going to go through with you guys and do that. So here's what we're looking at. Let's start with our f graph. What we want to notice is that through this section right here, from here to here, we are concave down. Okay, and at the top of this is a horizontal tangent line. And the place where I said we stopped being concave down, like right around there, that's called a point of inflection. And we're going to use that term quite a bit. It's where the graph kind of flips itself over. So a point of inflection. And then, because what happens then, from there to here, in this section, the graph is concave up. So that's why we called it the inflection point. And again, here we have a a horizontal tangent line. And then we can see these points on the other graph, on our f prime graph. So what we'll notice is where our first 0 is here corresponds to the x of our first horizontal tangent line. So where this point is right there corresponds to our first 0 here. So here, let's call this f prime of -1.1, that's going to equal 0, which corresponds, as I said, to where the horizontal tangent line occurs. Then what you're going to notice is this point right here at the very bottom of the graph corresponds, let me do that in red, corresponds to our inflection point. This is our point of inflection. And if you notice, it's exactly where the graph starts to change direction. So this is where our function changed direction. And then, of course, our other 0 right here corresponds to our other horizontal tangent line. So f prime of, let's call that 4.2 equals 0. So that's where our horizontal tangent line was. Okay? So that's what you're trying to see, the relationship between the two. We're going to finish our discussion of lesson 3 in the next video.